we're putting all of the force calculations that we've done so far and making sure we can figure out how motion can or won't result from these forces happening. So either all of these forces happening on this object will make it move, or all of these objects and these forces won't make it move. And so deciding between those two is trying to create all the net force. So when there's more than one force happening of all the 5 or 6 different kinds of forces we talked about, gravity force, normal force, tension force, elastic force, friction force. Was that all of them? It was most of them anyways. All the different types of forces, they all add together if there's more than one happening to them, and the net force is what decides if it's going to move or not. And if it is going to move, how it's going to move. In other words, what is its acceleration? Okay, so when drawing diagrams, which is the most important thing about this chapter, is drawing good diagrams. We do simple geometric shapes. Always shapes. I don't want to see shading or any perspectives. Shapes and points. Shapes and points. Forces, when we're drawing forces on them, we draw them with direction. We draw them in the direction they're going and with a rough magnitude, right? If one force is bigger than the other, magnitude. I can't multitask. I can't talk and say and write the word. A rough magnitude. Bigger forces should have bigger arrows. Smaller forces should have smaller arrows. We don't need to take a ruler and measure to the millimeter, but a visual difference between forces of different size is useful for you getting your intuition correctly. Forces are drawn acting on the center of mass. So all the forces that are happening on this object at one time, we are going to treat all of them as acting on the center of the object. Gravity is pulling on the center of the object. Friction is going to be shown in our diagrams as pulling on the center of the object, even though we know it's on the surface on the bottom, and so on. So even though the rope is pulling on one side of the object, we're going to show it like it's pulling from the center of the object. This just allows us to get our math right, even if it's less visually accurate. It's more diagram mathematically accurate. All forces are a fancy word, concurrent, which is a great word for all at the same time. So the friction force is happening at the exact same time as the gravity and the normal and the tension and the elastic, and all the other forces that could be happening are all happening at an instant. So this one thing is happening right then. And that's going to be most of what we're talking about. So those are just the summary of the things we've done before. And this is going to do, I got 4 different examples of diagrams for us to draw. And they go from, these are all pretty easy. These are pretty easy. So let's draw a few diagrams. A book at rest on a tabletop. So I will draw a tabletop and I will draw a book. There. Book on table. Now I will draw the forces that are acting on this book and table. So the forces are drawn in the direction they're going, and they're from the middle. So I'm going to draw my force of gravity pulling on its center of the book, which makes sense. I'm also going to draw its opposite normal force acting from the center. Now, I know the normal force is actually the desk pushing up on the bottom of the book, but we don't draw it that way. We just draw it from the middle so everything looks nice. And I'm trying to get my normal force the same size as my gravity force, but because in this situation, gravity force is equal to normal force. Why is gravity equal to normal force? Because it's not accelerating. I want to say that carefully. It's not moving, true, but it's also not accelerating. That's the key word. So F net is equal to normal force minus gravity force, which is nothing in this case. Let me slide up so everyone can see. But yeah, it's a very simple system, but it does correctly outline all the ideas that we're trying to get across. Normal force and gravity force are equal. The up equals the down. And so the arrows I drew on the diagram are the same size. In this next one, a girl is suspended motionless from a bar which hangs from the ceiling by 2 ropes. So I'm going to draw a bar, and that's it for the objects I'm going to draw. The rest is going to be forces. I'm going to draw one force over here and one force over here. These are my 2 tension forces on those ropes. And I'm going to assume that the weight in this case is going to come down here. That's a terrible drawing. I want to fix this. I want to make that longer. I want to make this one there. That's a bit better. Gravity force here. Tension 1. And we'll call it tension 2. Great. What is my net force equation in this case? Right. We're going to write both the tensions on top. And gravity down the bottom. Is this system accelerating? No. So we can write nothing for our F net. So this is why I had to change my drawing the first time. I wanted to say that, like, since I know all of the up equals all the down, so I wanted these 2 arrows to be smaller than this one, because I know tension plus the other tension equals the gravity. So I wanted to have that a little bit in the visual. The gravity arrow should be bigger, roughly twice as big as the other ones. Now, no one take a ruler on that because I'd run out of space. I don't think it's twice as big, but it is a little bigger, so that's good enough. You don't want it to be the same, because that would imply it's the same. Okay, a car is coasting to the right and slowing down. So I got to draw my car first. Draw car. There's a car, and it's rolling, so we need a ground of some kind. There's the ground. And what forces are happening on this car? One suggestion. Daniel. No. No pulling force in this case, because there's no indication. Specifically, it's labeled as coasting, so we're not engaging the engine of any kind. Caleb. Friction is happening. Why do you think friction is happening? What was the indication? The slowing down part told us friction. Good. What else is happening? Yes, it still is heavy. It has weight. And the last one, normal. There's ground, and so there's a normal force. And I think, oops, spelled N. There we go. That should do it. There's no forward force because with the coasting, it's indicating that there's no like engine force pushing the car forward. So we just have the slow friction slowing this car down. So in this case, the important piece is that our force net is not 0, right? There is acceleration. We are slowing down. So there is acceleration in this question. So in this case, what is the F net equal to? What is the only force acting on the motion of this particular object? Yeah, it's only friction in this case. So the net force is the friction force. So the rate of acceleration is entirely determined by the friction force in this case. And that's all we're going to be able to determine because we have no other numbers in this case, so this is as far as we go. It's just the diagram is all we're worried about right now. Next one is a very common program. So we're going to take an object. Oh, it's applied to a book. So it's basically the same book that we had in the first picture. Let's clean this up a bit. I want to put it a little closer to the top. I got a book. It's on a surface, and now I can put forces on it. It's heavy, and there's ground, so it's being resisted. It's being pulled in this direction. So I'm going to put a pulling force in this direction. There is a friction force in this case, which I pull from the center. I'm going to slightly adjust this to there. F, friction. Right. So what is different about this picture than many of the others? There's 4. Nikita, what else? There's acceleration. So how have I indicated there's acceleration in what I've drawn? Yeah, Max. That's right. So I made this one noticeably bigger than the friction force, indicating that there's way more force on this right side of the object. And so there will be a net force in that direction. So in this case, we know that the net force of movement is going to be Fp minus Ff, and it's not 0. So this will actually indicate some acceleration of some kind. Now this is in the x direction. There is also an F net equation we could write in the y direction. It does have a net of 0 because this book is not going up in any way, right? So in this case, according to my diagram and the sentence, the up force equals the down force. So it'll be exactly the same as this part in the up and down direction. All right, setting up the first one, an elevator with a mass of 945 kilograms is accelerating downward at a rate of 1.35 meters per second squared. What's the tension in the elevator cable? So I'm going to draw, oops, I don't want it red. I'm going to draw an elevator. And it's going to have a cable on the top of it. It's a very exciting elevator. Do I care what's in the elevator? Oh, this is it. It's all I care about. Let's put the forces on this thing. It's an elevator. It's heavy. So we're going to draw a force of gravity on it. And we know it's being held up by a tension force. That's it. That's all we know. Hopefully the elevator does not move sideways at all. That would be a bad elevator. So this is it for now. We next need to set up an F net equation. That's the next step. So what's all the upward forces? Force of tension. That's all that's there. What about downward forces? Gravity. That's it. So this is all that we have to start our question with. And now we'll do our algebra and numbers starting here. So this is we've done with the diagram parts. We can now do numbers. What's the goal of the question now? Daniel. So I'm looking for a force of tension. So I'm just looking for, like, this term here. So that's what I'm looking for. What is number belongs here? So the best way to do that from here is I'm going to rearrange this equation right now for Ft. Just going to solve for it right now. And so that means I'm just going to add the force of gravity to the other side. And so, oops, wrong color. I'm going to write F of tension is equal to the force of gravity plus the net force. Could have gone the other way because it's adding, but that's just take force of gravity, throw it over here, and add it over there. Do I know what the force of gravity is right now? Do I know that number? Not directly. So I want to go to the formula sheet. Can I break down force of gravity? It's M and G. So that's true. I know M and G. Do I know the number of the net force right now? No, it's not given, so I have to break down the net forces formula. That will be mass and acceleration. Okay, now I'm going to look at this line. Do I know the number for mass? Yes, I do. Do I know the number for G? Yep. Do I know mass? Same. Do I know the acceleration number? Yes. Okay, now I can do all the things. I can type in the numbers. So what are we going to do? We have a mass of 945 kilograms. G is still 9.81. We're going to add the mass again, 945. We could have done some factoring there if we really wanted to. And the acceleration is going to be, oops. Yeah, it's negative. 1.35. Good. Nice. There we go. Now we can type this into our calculator and cover it. The number out of a calculator is around almost 8,000, right? I think it gets to be 7994.7. That's a lot of numbers. I'm going to have to round some of these out. How many am I going to keep out of this thing? How many important numbers should I save? 3 important numbers. There are 3 important numbers, so this will be 7990 newtons. What direction is the tension force going? Up. So in this case, our answer is 7990 up. So almost 8,000 newtons up in this case. So we have our basic 4-direction system here, and we care about the acceleration of this object. Which direction is this likely to accelerate in? Yeah, that way, right? Well, that way. And so since the acceleration is that way, that's the direction I care about my F net. Is there an F net that goes up and down? Yup. I don't want to write it down. It's just going to get confusing. I only care about the acceleration in that direction, so that's where I'm going to start. So I'm going to start with my F net in the direction, in this case, the x direction. That's the one I care about. So what is the force making it go forward? The force of push. And is there anything else making it going forward? Nope. What's making it go less forward? Friction. It's a force acting in the backwards direction. I can't say it's making it go backwards because friction can't do that. But what force is acting in the negative direction is friction. And we know that it won't be 0. Okay. We're looking for our acceleration term, right? This is what we're looking for right there. So it's already where it wants to be. It's almost isolated. It's on the left side. It's where it is. I don't want to do any more algebra with it. Do I know the value of FP? Yeah, I do. It's in the question. It's 95. So I know it's right in the question. I can write 95 newtons right here. Do I know how much the friction force is? Yeah, so I don't even need to break out mu or anything like that. I just know the friction force is a 50. That's easy enough. So the net force in this case is going to be a 45 newtons. That was easy enough. But I need to figure out what the acceleration is. Do I know what the mass of this object is? Yeah, cake, right? So acceleration will just be F net over m. So 45 over 25. I guess that's technically 0.0 on all of these. I lost all of my significant figures. So we're going to get 3 out of this. So what's this? 45. 25? It's 180, right? Yeah. So I get 1.80 meters per second squared. Why is that 0 there? Sig figs is true. There are 3 in this whole question. That's 3 in everything, so the answer has to have 3. Even if it works out to a nice, almost round number of 1.8, we got to add that 0 in because we do know that 0 is accurate. All right, so this is about as detailed as I ever want my diagrams to be. Basically, it's showing, I want to do this specifically more for the explanation. This is about as detailed as you ever want to get. But because I want to look at this particular sentence right here where it says, what is the reading on the scale? So my center of attention in this whole question is this here. What is the scale doing? Everything else is context, which is sometimes important, but we want to make sure we're not putting the center of mass here on the person or in the center of the elevator. It's the scale. So what is the scale going to experience? So what is making the scale do all the things? So the scale has a force of gravity, this total force on it. It's reading the person's weight. So we're caring about the person interacting with this scale. Oops, I want that back to the right color for my forces. So I have a gravity force pushing down here. I have a normal force pushing up here. I don't have any left or right forces in this case. So sometimes it's useful to throw, where is the A going? So is the A going up or down? In this case, it's up. So we're just going to draw an arrow on it just to put in our context it's up. Because that tells me I know my net force is also in the up direction. That's what's useful about that. So if I know my net force is in the up direction, how is the normal force related to the gravity force? Set up the F net equation. So our F net equation is the same as it almost always is Fn minus force of gravity. So, as I will point out again, this negative here accounts for gravity going down. So now that we're going to algebra this around, the fact that G won't be negative later is fine. It's already set up to be negative here, and any other algebra we do on that is just algebra, it's just math. But in the diagram, the down arrow is covered by this negative here. So now what we're going to work with is trying to rearrange for Fn. So if I rearrange this equation for Fn, what do I get? Yeah, I get to add the two together. F net plus Fg. So now that we've rearranged it, it does feel like, is gravity positive all of a sudden? No, gravity is still down, but we're adding the two sizes of the two forces. The size of the F net force plus the size of the gravity force add together to make the normal force. In other words, the scale is reading how heavy the person is plus how fast it's moving. Right? It's doing both of these things. So we guessed ahead just by the description that the scale should read a higher number than the weight, and that higher number accounts for the weight plus the acceleration force. Those two forces added together are going to account for my normal force. Now we can put in our numbers. The net force is going to be ma, and the gravity force is mg. So we can now put all the numbers we want in here. We know that this is going to be 72.0 times 0.80 plus 72.0 plus, times 9.81. Uh-oh. 9.81. Great. And now we can get our calculators in order to get this number. I think it is 763 3.92, bunch of numbers. After that, we're not going to collect all of them. How many are we really going to keep? It's 2 in this case. It's 2 from this one over here. This one is only a 2. So right here we have 2 only, so we can only keep 2 only. So this is a 760 Newton force. Remember, this is also known as apparent weight. We feel this normal. Like when the elevator starts going up, we will feel that heaviness on ourselves. So that extra force we feel, that's our apparent weight. So it's not our real weight, that's just our force of gravity. But our apparent weight is the other one. I'm going to go through this whole thing. So this system is a crazy system. It looks really complicated, but it really works out easily once we can see the idea. Now, the idea is what is going to move in what direction is the goal. So if I hang this weight off this object, what will happen? Right? What's going to happen with these objects? There's exactly 2 options. What's one of the options? It could fall, right? The one on the table will move to the right, and the one that's hanging will go down. What's the other option? They could stay perfectly still. The friction could hold them stay. That's totally possible. So we got to figure out which one of these 2 options is available to us by figuring out what forces are going along. So the key here is this pulley. The pulley, all it does is it changes the direction of the force. So this rope is pulling to the right, so I'm going to put this on here. I'm just going to draw the first force here. We have a tension force here, and it's pulling this object to the right. And now what this pulley is doing is it's changing the direction from horizontal to vertical. That's what it's doing. And so now this rope is pulling this weight up. So I'm going to put that one on here now too. We have this one here that's pulling it up. And what did we learn about tension in the last lesson? Tension in the same rope is equal. So how much is this rope affecting the motion of these objects? It's not affecting it at all. So the rope is just transferring the force. It's just a connector at this point. The tension in both ropes, it's equally in both directions, and so it won't overall contribute to the motion of this object. All right, let's get some more forces listed on these objects. Let's start at mass number 1, the one on the table. What other forces are happening on this object number 1 on the table? Friction is happening, that's true, because I showed there's a coefficient of frictions listed below. What else is happening on the one on the table? Gravity and normal is also happening on this one. So I have gravity here, and I have normal here. Now, on all of these ones here, on the table here, I'm going to put 1, a 1, and a 1 on both of them. Because they are relative to the mass number 1. And so the bottom one is going to have a force of gravity on it. But I'm going to call that force of gravity 2, because it's different. It's based on the other mass. And they're not the same. They're close, but they're not the same, and so we have to treat them differently. And so what we actually are going to work with here is the net force. Let me write this here as a sentence. Force net is along the line of motion. So it's where things will move. So it's along the connection. So the force net actually goes from here and then turns and goes down. So my F net is this here. It's this whole thing, all the forces that are in the direction of movement. And so the pulley allows my net force to actually turn. My net force actually turns around the pulley. That's what the pulley is doing in this particular example, is it's changing the directions of our forces. So what are all the things that are in the net force? It's this one, and this one, and this one, and this one. All the ones that are in this line are in the net force. Now, what gets weird is which direction is the positive direction when we start changing the direction with pulleys? And the short answer is, I'll just skip that right there, is it doesn't matter as long as it's consistent. So we basically need to pick one side as positive and one side as negative, and then just keep it that way, and everything else will be fine. So we tend to like the bottom being a negative, so we tend to put this one as a negative, and we tend to put this one as a positive. There isn't a correct answer. It's just now anything pointing towards the positive is a positive force. Anything pointing towards the negative is a negative force. So that's the criteria that we have now. So let us just go from left to right and list all the forces in what direction they have. According to the diagram, this force of friction, is it positive or is it negative? It's positive in this case. So it's pointing towards the positive direction. So we're going to put in force of friction 1 as a positive force. So moving along the line of movement, the next one is this force of tension. Is this a positive or negative force? This is a negative force here because it's pointing towards the negative. So this gets put in negative Ft. The next one here is this one. It's pointing in the positive direction. So this one will be positive Ft. And then the last one is a negative force of gravity 2. So this is my entire list of my forces in this diagram. But you guys have already heard, I've heard you guys murmuring, these two forces cancel out, don't they? Because they are the same size in opposite directions, they cancel out of our expression, so we don't care. So we can simplify our force net equation is equal to the force of friction in 1 minus the force of gravity in 2. So that's the only things causing this to move. We're basically balancing how much is this pulling down versus how much is this trying not to move, right? That's the thing that's going to decide how much this is going to move. Do we think that this is going to move or not? Yeah, it's definitely going to move. The frictions are not huge. They're all less than half. The weights are roughly the same. It's going to move. So we're going to just shortcut us there and use the kinetic friction to do our math. Let's put our F net together. Force of friction is going to be mu K Fn minus mg, or m2g. So Fn1. Okay. So those are all the numbers we got to throw into our equation here. So mu K is 0.310 multiplied by my force normal, which is just my mass, 5.50, and gravity, 9.81. And I'm just going to slightly shift, or can I do it this way? I can slide to the side here. Minus the mass 2, 5.20, multiplied by 9.81 again. So that's all the numbers being thrown in here. It's very good. So basically I can start pushing the numbers out of this one. All I get here is 16 something to 6, bunch of numbers. Subtract 51.012 and extra numbers there. So this is confirming my initial prediction. This is the down force. This is the up force. 51, significantly larger than 16. So this is definitely going to accelerate down the hill. This is going to slide off the table. It just will. The kinetic friction is like 0.3. That's like roughly what you guys found on the tables here. If you put two weights of the same size and put one on this table, it'll slide right off. It's not that different. Okay, that's great. We do the math on that, and we get, what do we get? A total F net of, that doesn't sound good. 126 minus 51.012. Oops, I did that wrong. Let's fix that. Minus 34.286. Bunch of numbers. Close enough. Great. What do I care? What do I want? That's the F net. I got a number in newtons. What's the goal of the question? Acceleration. How do I find acceleration? Acceleration is F net over m, right? What's the mass of this thing? It's 10. Why is it 10? Because what is moving? Which block is moving? Both are moving. So both go into the mass here. So we get the 34.286 over the 5.50 plus 5.20 together. So we get minus divided by 10.7. 3.20 meters per second squared. And it is down and to the right, depending on which block I look at. So I can use, since the system, the pulleys, are exactly the same as they were in the previous question, I can just use this right here. Just start here. Everything else goes away. We're just starting right here. So since it's basically the same question, I can go F net is equal to F1 minus force of gravity 2. And I know that it's 0 because it won't move. So because it won't move, I know these are the two numbers that are the same. So this question is actually really easy once I've set up the equation. So now that I've done all the hard work in the last part, now that I have this set up, it's really easy. So I can also say that the force of gravity in 2 is equal to the force of friction in 1 because they're equal to 0. I can just algebra that one to the other side. So I'm going to put down all the equations because I'll show you another quick trick. Is if I know this is M2 with a G, and this is equal to mu M1 with a G, what do I see that I don't care about anymore? I don't really care about G anymore. You can get rid of that. That's one less thing to deal with. It's not hard because we know the number. It doesn't really matter, but it's one less thing to put into your calculator. So now I can see that literally the only thing I have to do is M2, the goal of the question, is just equal to mu and the other M1. That's it. So which mu am I going to use in this case, S or K? So I have to use the S one in this case because we are trying to make it not move. So we have to use 0.440 multiplied by M1, 5.50 kilograms. That's it. 0.440 times 5.5, done. And I get 2.42 kilograms is how big it can be.